let's summarize what we have learned last time. So basically, we talked about the change of variable in double integral, actually in multivariable, integral. So let me write down the formula and then explain more about the integration by substitution. So first of all, let's say we want to integrate a two-variable function on domain D which lies inside xy plane. Then, assuming that we have a transformation from E to D, where E is lying inside of UV plane, and I can write down every point in xy plane uniquely in terms of UV point, then I can rewrite my integration, which gives the same result as the following. So first of all, I want to evaluate the same value of function f, but instead of putting x comma y, I'm putting u comma v. That is translated into point in xy plane by the transformation function. So that's why we need a composition of f and t. And then instead of just putting du dv, we need to modify the ratio between the area in xy and corresponding area in uv plane. So that correspondence is the Jacobian. Usually they put Jacobian, absolute value of Jacobian, but we define the Jacobian to be the absolute value of determinant, so it doesn't matter. So let me give another notation. Usually what people do when you do the integration by substitution is the following. So instead of introducing the symbol transformation, they simply use, they actually have to use the transformation t here. But instead of jt, the Jacobian, they simply write that as the following. So let me say this is another symbol for Jacobian. So why do I talk about this symbol? Because it's kind of easy to remember what to take as a partial derivative if you write this way. Because we want this form, dx dy, but instead of integrate over x and y, we want to integrate over u and v. Then we need somehow eliminate du dv with the denominator so that we get dx dy. So you can kind of remember that we will get, after having this factor, this delta uv cancel out with du dv, so we are left with delta xy, which gives the dx dy. Okay, so and then this dxy over duv is easily remembered as the 2 by 2 matrix, where you have x and y in the numerator. So we're going to take xy function in terms of uv, and then you're taking uv as a derivative variable because it's on the denominator. So this is xu, xv, and yu, yv. Again, remember that this is not a constant number because this involves u and v of variables. So, and also we are going to take a integration over the domain E, which lies inside of UV plane. So UV changes over E. Okay, so you will get a formula in terms of UV, and with the multiplication with f composite t, which is also a function of uv. So this, let me write above here. So this is a function of uv. So we basically have entire integrand of this new integral as a function of uv, which is the two-variable function. So why we do use this substitution? Because sometimes it's harder to use the original variables to integrate, but if you change your variable to new variable with some substitution that makes the integrand easy, then it is possible to take the integral. So if you apply that to the triple integral, then you can do the similar. So if you have a three-variable function and you want to integrate over some volume v inside of x, y, z space, then you will need a transformation that maps w to v, where w is a domain which corresponds to v by one-to-one mapping of called t, and this makes w integration, or the integration over w, and we want the same value, but we are using a variable in w, so we need a composition. And then we can also write, let's say, this t maps u, v, w to x, y, z. So u, v, w is a point in w, the large w, and x, y, z is a point in large v. So what we have to multiply as a factor is the Jacobian given by this form. So we're taking a 3 by 3 matrix, and x, y, z is a function to take the partial derivative, and u, v, w is the variable to take a derivative with. So we have xu, xv, xw, yu, yv, yw, and zu, zv, zw. So this is so determinant of this matrix, right? Determinant of this matrix. And then you take the absolute value here. Right, so, and then you need du, dv, dw, okay? So again, these are just a function of u, v, w, and then multiply with the formula of f, and then you get integration over u, v, w. So as an application, I'm not sure it's really a direct application, but basically I don't want to give an example that practice you as like as a technique. I want to give you an example that really uses the nature of this substitution. So I want to introduce an interesting theorem. Actually, it's a theorem that appears in the Dukarmu's book on differential geometry. But it's easy, so that anyone who understands the multivariable functions and this double integral and substitution can understand this theorem. So this theorem is by, it's called Cauchy-Crofton formula. So what does it say? So let L rho theta be a line. It's a straight line, like infinite line, on a plane, R2 plane. So rho and theta is a parameter to determine the the line, but that's, we already have seen that, because how we're going to parameterize is the following. So we first take the distance from the origin to the line. So that's going to be the rho. That's going to be the rho. And the angle between this perpendicular line to x-axis is the theta. So once you know what rho and theta is, you can determine the line. So I'm not going to explain that in the words. So we are going to assume that rho is always positive. Okay, that's one condition. Theta is from 0 to 2 pi. So far it's not interesting, just the parameterization of a line. And let's say, let C be a curve in R2. So it's a different curve. So L is just a line parameterized by 2 parameter, and C is just a random curve. And let n rho theta be the number of intersections between C and n rho theta. So let's see, we have a curve on xy plane, like this curve. It doesn't have to be closed curve, just any curve. And we count the number of intersections. So for example, this line, L rho theta, intersects the red curve twice. Okay, so the n is 2 when rho and theta is given in this configuration. So if you have a different configuration, you could have a 3 or more, maybe not more, just a 3 or 1 or 0 sometimes. So anyway, that's just a number, and what we compute is the integration. So integration is over theta is from 0 to 2 pi, and rho is from 0, always positive. Okay. So, and then we'll integrate this function, n rho theta, over d rho d theta. And surprisingly, the result is twice the length of curve. So you don't have to worry about this unboundedness of rho, because if you have a curve, if it goes infinitely long away from the 0, then obviously the length of curve is infinite. You're not going to measure anything. So we kind of assuming that this curve is a bounded curve. Okay. Otherwise, there's no point of getting a length, right? So if it's bounded, then you have a bounded range of rho that intersects this curve once you have this parameter rho and theta for some line. So your range of rho that has non-zero n value is bounded. So you will eventually get some bounded interval for rho, so in order to have non-zero n. So you don't have to worry about this unboundedness of region. So what does it mean? Okay, so the proof is a different issue, but I want to explain the implication of this theorem. Suppose that you have a curve, or you have an image of a curve in a file or something else, and you want to measure the length of that curve. Okay, so you're suppose that you're given with a paper where the curve is drawn on this paper, and you should find out the length of the curve. How would you do that?
Length of curve in the paper.
Yes, drawn in the paper. Anyone? Anyone else?
Divide
Hmm?
the whether we know how to measure the length on a polar curvature. I mean, we can use a polar equation.
Polar equation, but it's just drawn picture. Okay, so you don't have an equation. So you have a piece of paper and then some randomly drawn curve, and then you try to ask someone else to find out length of this picture. So one way you can do that is you just prepare a string, and then you just lay out your string, which follows this curve, and then after you finish, after you start with the one point and then finish at the other, and then you try to stretch your string, assuming that this is not a rubber string, that the length of string is the length of curve, right? But that's very elementary way of measuring the length. Another way is you can use, if you have a ruler, a straight ruler, then you can subdivide your curve and then try to measure a straight line distance between the 2 points, consecutive 2 points, and then try to approximate your length of curve using the sum of lengths of each line segments, right? But that's not the actual length. So, and both ways are kind of ad hoc method. You can do it on your hand, but if you cannot program it. So, what this theorem says is that, let's try to look at the left-hand side. So left-hand side says that you are taking integration 0 d zeta, and this is approximately same as sum of all n values with parameterized rho and zeta. And this d rho d zeta becomes delta rho delta zeta if you take not infinitesimally small rho and zeta, just a small value of small change of rho and zeta. This becomes a fixed value, but really small, and you're going to take all the possible n's with change of rho and zeta with increment of delta rho and delta zeta. But let's say I take fairly small, but not too small, so that I can measure the distance between this line. So, which means that I take a rho equals to 1/10, like 0.1. So I didn't give any scale here, but let's say we have like 1 minus 1 here and 1 minus 1 here. Then I'm dividing into 10 pieces in each directions. Or maybe more, but I have to cover entire curve here. So anyway, so I can fix this number, and also I can fix my increment of theta. Let's say I want it pi over 4. A small is good. A smaller, the better, but I can only do this because I want to draw the picture. So what I'm doing here is that starting from rho, from negative infinity to positive infinity, but actually I don't have to cover entire range because it's bounded. So maybe I can cover it from -1 to 1, as long as it contains entire curve. And then I can also change my theta from 0 to 2 pi with increment of pi over 4. I just measure the number of intersections for each lines. So let's say I take rho from -1, -0.9, and so on until I get plus 0.9 and 1. And I fix my theta to be 0. So when theta is 0, I'm taking a straight line, vertical lines, right? That's how I do this, right? So sorry. So, by the way, I didn't say that I don't want this negative values, right? So I just take 0, 0.1, 0.2, and so on. Because I assuming that rho is always positive, so I just take this part. And then that means, let's say, I cannot draw 10 of them, so just understand what I'm doing here. So I have this much of lines here. How many? 1, 2, 3, 4, 5, 6. Okay, I think I should put more here. So more. 7, 8, 9, maybe 10 here. Okay, so there's 10 lines, and each line intersects the curve in a different points, and the number of points that intersects is 1, 2, 3, 4 for the first one, or maybe not. Maybe the first one is here, so I just put here. So since I put 0 here, so first one, 1, 2, 3, 4, and the second one also intersects at 4 different points, and third one intersects only 2 points. You're adding all up, okay? You just take the number of intersections and so on. So here we have 2s and 2s and 2s. Just count the number of intersections, okay? So first, count the number of intersections of line rho theta by changing rho from 0 by delta rho and theta from 0 by delta pi, delta theta. So basically, if you reverse the order, take the theta to be pi, then you're taking the opposite direction, opposite side here, right? 10 of them, okay, and so on. So we have somewhere here, right? You just take the number of intersections and so on. And then if you want to change the theta, what you can do is, now we have a vertical lines. You rotate that by 45 degrees, and then you count the intersections again for each line. How many intersections for each line, and you just add all these numbers of intersections. Okay. And you do this for 8 times, or maybe not 8 times. Okay, so maybe because if you take the both sides in a one cycle, if you take the one step as a both side, then 1, 2, 3, and 4 times is enough to cover entire cases for theta from 0 to 2 pi, right? So you have 4 steps of measuring and counting the intersections, and you compute this number. Delta theta is fixed, delta rho is fixed, delta theta is fixed. Just count the total number of intersections after you do this 4 times of measuring the intersection, and that's the approximate 2 times of length. Let's look at the example. Yes.
Should we include
2 pi.
in 0 and zeta equal 0 and zeta equal 2 pi?
Mm-hmm.
Just be the same?
Yeah, you can eliminate one of them. But as I said, adding one point in the integration domain doesn't change the integration because it doesn't have an area, right? So it doesn't matter. Okay, so for example, let's try to approximate the length of a circle parameter. Let's say I have unit circle on xy plane. Now I can range my rho from -1 to 1, 0 to 1, and zeta from 0 to 2 pi. Basically, if I do that, then let's say I take a net of set of lines, and I'm going to rotate my set of lines and then measure these intersections. But this is a symmetric picture, so if I rotate the set of lines, then it will have the same number of intersections because it has the same configuration between lines and the circle. So let's say I have rho equals delta rho equals to 0.1 and delta theta equals to pi over 4. What happens is, how many lines do I have? If I take maybe 0.1, that's fine. So maybe I can make it more abstract. Let's say 1 over n. And how many lines do I have here? I'm taking -1 to 1 here. So if I take half of them, it's n plus 1. But I have another half here. So we have 2n plus 1 lines. Okay. And except for the leftmost side and the rightmost side, we always have 2 intersections, right? So if I count the number of intersections, how many intersections are there? Right, 2 plus 2n minus 1 plus 2. So it's 4n, right? 4n intersections. So let's compute this integral. That integral over domain. I'm not going to write the domain here. If you want to, you can write it. So let's say rho is from 0 to 1, and theta is from 0 to 2 pi, and rho zeta, d rho d zeta, which is approximately, I'm taking all the number of intersections, and for each theta, I have 4n intersections. So 4n intersection, that's the a total number of n, because we have a fixed delta rho and delta theta. Delta rho is 1 over n. Delta theta is pi over 4. And how many set of lines do we need to cover entire cases? As I said, since we are taking a negative case together with the positive case, we have 1, 2, 3, 4 is enough. So we have 4 summation required here. So basically it's 4 pi. That's 2 times 2 pi, right? Okay. So it's not a coincidence to have twice of the length of a circle. It's because of this Cauchy-Crofton theorem. The reason why we have actual value instead of the approximate value, although we had this approximation sign, is that the circle is symmetric. Okay. So let's prove this Cauchy-Crofton theorem. So this is very useful when you program something to measure a curve on a planar image. So basically, you don't have to try to find an equation of a curve or try to like analyze the pixel-wise movement of the curve. You just try to count where this curve intersects with vertical or slanted curves, slanted lines. So let's prove. So maybe this is the first time I prove something in this course. But the proof is very interesting. So whenever you try to do something, try to make it in a very special form of the theorem. So we have a general curve in the statement of theorem, but let's take very, very special types of curve. Let C be 0L cross 0. That means I'm taking a straight line segment on x-axis with length L. Okay, that's our C. And try to compute my integration. Then, so I'm not going to write this bound yet because first let's make it a Fubini theorem here. How long can how far can theta go? So in order to make an intersection with line and this line segment, my line cannot be here, right? So if theta is bigger than pi over 2, then it doesn't intersect with this line segment, right? Or if it's here, means that if it's still not less than 2, if it's still less than 3 pi over 2, it doesn't intersect. So only cases that this line segment intersect this yellow line segment is when theta is from negative pi over 2 to pi over 2. Okay? Although I made the range of theta from 0 to 2 pi, I can change it to minus pi over pi. So let's say I'm taking theta range to be minus pi over pi. So in order to have an intersection, which means that in order to have non-zero n, my theta should be at least bigger than minus pi over 2 and less than pi over 2. And in that case, let's see, let me make it bigger picture here. So here is our theta. How far this rho can go? So rho can be 0. That means it intersects at origin. Rho cannot be bigger than this because if it's bigger than this line, then it will not intersect this yellow curve anymore. So let's see, the upper bound for rho is when the line intersects at the endpoint of this yellow line segment. So therefore, since this line is L, what is rho? L cosine theta, right? So rho can from 0 to L cosine theta. And then what's the number of intersection? 1, always 1, right? So it's 1 d rho d theta. So what we get is minus pi over 2, pi over 2. And this is the integration over rho L cosine theta d theta. And L is constant. And what do you get when integrate the cosine theta from minus pi over 2 to pi over 2? So you integrate this sine, half of sine curve, you get 2, right? So it's a 2 times of this line, length of line segment, right? Okay, so we proved for the very special case. So how do we generalize? You can approximate any curve with a series of line segments connecting 2 consecutive points on this curve. So let's C be approximated by let's say Ci plus 1, or I from 0 to n minus 1, where so C is already introduced in the previous, I'm sorry, so maybe let C be a curve in R2. So this now it's a different C, okay? And then let us approximate C by a line segment. So whenever you write something and then you introduce some symbols that is not defined in previous sentence, that you have to explain what that is. Where Ci is the C Ti and Ti. So I have to reintroduce again. So let me, if you can see this correctly, let me write it again here. Let C be a curve parametrized by Ct inside of R2, where T is from A to B. Okay. Then I can erase this. So Ci is Cti, where Ti is A plus I delta T, where delta T is equally spaced time over A to B. So I'm trying to chop up this curve with the same direction, same length of time. Okay. And what I mean by this bracket is the line segment connecting Ci and Ci plus 1. So I'm basically doing this. So we have Ca to a curve connecting Ca to Cb. I'm trying to divide this curve with equally spaced time, and then try to take a line segment connecting these points, okay, and then approximate my curve using these curves, a set of these line segments. Okay. Now, then the length of curve is approximated by sum of lengths of this line segment, right? obviously. If you really want to go rigorous, then you have to prove why it's approximate, meaning that if you make n goes to infinite, why the sum actually goes to the limit of length of curve, but let's not do that. Anyway, then what we have to do is just separate all the cases of this line segment. Okay? So what we are doing is taking the number of intersections with the curve C. But we can say that C is a composite of these line segments. So what we have to do is try to compute the intersection count the number of intersections of lines with this line segment, Ci to Ci plus 1, and then do that for entire I from 0 to n minus 1. Okay? So we're going back to here. We have seen that the theorem holds for this special type of line. What if we move my line segment into different formation? So let's say let T be a one-to-one map. So R2 to R2 be a translation with rotation map of the line segment 0L cross 0, which means that I want to get a line segment, for example, this line segment, which is connecting Ci to Ci plus 1, by translating a curve, if the length is L, or Li, by translating the curve on a straight line segment on x-axis. How do you do that? Well, you can do it in many ways, but let's see. So first of all, you can translate your curve. Right. You can translate your curve Ci to Ci plus 1 first by take the rho, which is the distance from the origin to the line segment, to be 0, and then translate back to whatever the line that intersects the origin, and then rotates that again. Or you can maybe you can do it opposite way. Maybe you can rotate again and then try to pull back to the origin, the line segment that intersects the origin. So whatever you do is the change of rho and theta. Okay. So you have a line which you can take as a part of a line, straight line, infinite line. What you are doing here is change of rho and theta. So this is possible. The T is obtained by changing rho and theta of the straight line of the line L rho theta that contains the line segment ci plus 1 by, so changing this rho theta by a constant. By constants. So we need two constants, right? So this is, let's say, rho and theta, and this line segment is, this line is L rho theta. By changing rho and theta, you can make it into the line which is equals to x-axis, and then you can translate a little bit more to find out the length, right? To make it into actual equal to 0 to Li. So basically what you're doing here is you just change your rho and theta of the line. This translation is changing rho theta by a constant. So rho is mapped to rho plus, let's say, rho 0, and theta is mapped to theta plus theta 0. So why we care about that, what we are going to do is try to use the, we try to apply this theorem for each of line segment, and then if you sum all up, then it becomes the length of the curve. So by observing this argument, this implies that the Jacobian of this translation, in terms of rho and theta, so we are going to use the rho and theta for the previous domain, and after we have translated equal as this previous one. So this is because this is basically determinant of, so we are going to take a new variable, partial derivative with the old variable, and also, rho plus rho 0 with theta. And the second variable, which is theta from theta 0, and we have partial derivative, and also we have theta from theta 0, partial derivative. So I didn't introduce a new symbol here because it's going to be a redundant. So anyway, our new function is simply old variable plus some constant. I'm going to take a partial derivative with old constant. What's the result here? 1. So how about this? 0 and 0, 1. So basically 1, 1. So it's identity matrix. If you take the determinant of that, it's 1, right? So if you take the integration if you take the integration of, let's say I give a name for this. So let's say n1 rho theta is the number of intersections of line segment ci plus 1 with line arrow theta, and n2 is the same with the trivial line segment 0L, let's say 0Li, with lines L or theta. Then if I define n1 and n2 that way, then whatever I do to compute the n1 rho theta is trying to find the intersection with this line segment of some other line segment, right? So this kind of line segment, L rho theta, intersects this line. But to find out the intersection, it's the same way we find the intersection with this curve, this line, and this line segment, is that after we translate my rho and theta, entire for entire line segment and these straight lines. And it's same as finding the line segment with translated straight lines and this trivial line segment. So here we have something like this. So when you translate this line segment to here, then we can also translate these red line segments to this green line segment. And everything is same except that we just translate my rho and theta by constant numbers. Okay? So when we count the multiplicity, this is actually equals to counting the multiplicity because Jacobian is 1. So this implies that counting this, measuring the length of this straight line segment on any configuration is obtained by taking the integration of intersection over any line segment that intersects it. Okay? So that's one observation to finish this proof. So since this Cauchy-Crofton theorem holds for any configuration, any line segment in any place in two-dimensional plane, we can say that the integration for integration of ni, where ni, let me write it again. So let's say ni rho zeta is number of intersection between the line segment ci plus 1 and the line L rho zeta, then the Cauchy-Crofton formula holds for this line segment, the rho d zeta, is 2 times of ci plus 1. And let's add all left-hand side and right-hand side for I from 0 to n minus 1. What happens? Maybe I should write it here. So what happens here? So when you add all indices for the left-hand side, you're counting multiplicity. So if you add all ni, what you get is total number of intersection of between the entire curve and the line segment, straight lines. So so it's like a total number of intersections between this C and line, right? So basically what you get after you sum over left-hand side is just the original integration. You just take all the intersections with the curve. Basically, so sorry. So this is not exactly C, but it's that one, union of ci plus 1 for now, because we are taking a sum of segments. So and then what happens to the right-hand side when you sum over I? You get this, right? So this is equal to I from 0 to n minus 1 of length of sum of lengths of these segments, right? So and then what we do is taking n goes to infinity. So we're taking smaller and smaller pieces of line segment to approximate the curve. So that becomes the left-hand side. So this left-hand side becomes integration over nth rho theta. Now, this time, this n is number of intersection between C and the line. Okay, so it's a different from the last definition. So we had in this equation we have an intersection between the set of line segments with the line, but when we take the limit n goes to infinity, since the segments, sum of segments, set of segments, the union of set of segments is becoming entire curve. So we have actual intersection between curve and the line. And what happens to the right-hand side? So right-hand side was the sum of lines, sum of lengths of line segment, but we observed that when n goes to infinity, that it actually becomes the length of entire curve. So this part becomes the length of curve. I'm sorry, so I put 2 somewhere. This is 2 times the length. So this should be 2 times the length. Okay? So that proves the theorem. That's the end of it. And you have to note that the essential part of proof is this change of variables. Like you change the rho and theta, it doesn't change. You have to use the integration by substitution, but the Jacobian is 1, so that means the integration doesn't change. Our integration is same, always the same, but the integration, the way you integrate is always the same. That's the main point. 네. Okay. So I didn't want to erase this, but I can erase this. Okay. So, all right. So let's say ni rho theta, the number of intersection between the line segment ci plus 1 and L rho theta, then if you take the usual Cauchy-Crofton formula, it holds for any line segment in any places, right? So we have ni rho theta d rho d theta is equals to 2 times of length of ci plus 1. And let's take the summation from I from 0 to n minus 1. And this is n minus 1, length of line segment from ci to ci plus 1. So we know what happens to the right-hand side here. So it's sum of all line segments. So approximately, it approximates the line length of curve when n goes to infinity. But before we do that, let's talk about this part. So I didn't put any, I didn't specify domain here. But let's say the domain is just the entire domain, okay? So that means I'm counting all possible intersections with any line segment because I'm taking I from 0 to n minus 1. So if I take, I can take this summation inside of this integration sign because this rho and theta is just moves freely around. Okay? So when I add all ni's, that means if I take one line segment parameterized by rho and theta, I'm taking intersections with any line segment from Ci to Ci plus 1 for any I, right? So for example, if I have this Ci, Ci plus 1, Ci plus 2, and so on, so it goes on here, and my line segment looks like this, then I have ni rho theta equals to 1. This number of intersection is counted in here, and also there's one more intersection with a Ci plus 1 to Ci plus 2. And there's another intersection with line segment Ci plus 2 to Ci plus 3. Okay? So ni rho theta is 1, and ni plus 1 is also 1, and ni plus 2 is also 1. So there could be more, but I'm not talking about the entire string. Just talking about these three means that if I add this all up, it becomes 3, right? 3 intersections. That's what I'm doing here. So I'm taking all intersections for any line segment. Okay? So let's say n rho theta is the number of intersection between the line segment and the entire set of line segment. Okay? So if it intersects any line segment, then I'm going to count that in this number. Okay? Here I separately viewed my intersection for each segment, but I'm going to take it all into one. So then the left-hand side, this becomes left-hand side of becomes n rho theta d rho d theta. Okay? And then what? When you take n goes to infinity, now this becomes, so left-hand side is now become, now the n is changing. So n is the number of intersection between rho and the set of this line segment, union of this line segment. But if I take n larger and larger, this union of this union of line segment is not equal to C, but it's approximately equal to C when I chop more points. So left-hand side now becomes the same formula, but the meaning of this n is different. So n is now becoming the number of intersection between L rho theta and what? C. Let me put it red color with C. So instead of this, we have C. Okay. So how about the right-hand side? So you have sum of 2 times the sum of length of each segment, right? That's becoming entire line, length of entire line. That's the formula. That's the Cauchy-Crofton formula. Okay. Any other questions?
Can you say
why we have 2 times of LC?
Why we multiply 2?
Why do we multiply 2? Good question. I erased it, but when we cover the case for 0L, a straight line on x-axis, we had 2 times of L on the right-hand side. That's where it came from, right? Okay. So if you trace back where this 2 came from, it came from at the observation of the very special case when we deal with the line segment in x-axis.
Can you explain one more time more elaborately? Because I was wondering, I think it is the same question, but I have a question about the most upper equation.
What, this one? This one?
Yes, that one. Well, we actually obtained that equation from the previous observation. That one lies on the x-axis,
Mm-hmm.
one is on
Mm-hmm.
the xy plane. But I still don't get it why. It is quite ambiguous to me to find the connection between the observation and that equation.
Okay, so let's make it concrete. All right. So we are at the space of lines, okay? So we are talking about the line parameterized by rho and theta. So we are talking about the rho and theta. I'm going to introduce a translation function. So let me make a concrete example first. So if I want to translate a line segment, let's say pi over 4 and 1. So it's L of 1 pi over 4 to a line segment which is just x-axis, which is, let's say, you can say this is 0, 0. What you have to do is translate. So I'm not talking about translating the point. I'm talking about translating a line. So that means I have to translate my rho and theta. Okay? So that's a different point. So I'm not translating each point here. I'm translating just these lines. So this is the line in xy, which is actually parameterized by rho and theta. So this line is matched to rho equals to 1 and theta equals to pi over 4. So the entire line corresponds to 1 point here. And this one corresponds to 1 point in the origin in rho theta plane. What I'm trying to do is find transformation T on here in rho theta spaces, between rho theta spaces. I want to translate this point to here. Okay? Just take rho to 0, right? By taking rho theta to rho minus 1, comma, theta minus pi over 4, right? So let's talk about this transformation. That transformation, okay, so let's say we have same degree but different distance. What does it translate? What does this T translate this green straight line to? right, so here. Yeah. Okay. So accordingly, if we take this transformation on rho theta space, we're going to translate all line in the same way in xy plane. Okay. So what we are trying to do is try to, let's say, say we have a line segment on here. I'm going to translate that to, sorry, I should put that in the red curve. So if I had a curve here, line segment CI to CI plus 1 from here to here, I'm going to translate that to here, right? So how I do that is by taking this transformation of rho and theta. Okay, so if I translate that, maybe I don't get a line segment actually starting from the origin. Maybe it should be somewhere like here, but it doesn't matter. You can easily show that if you move your line on x-axis, you get the same formula. That's something you can do more extra. So anyway, suppose that you did that, then this transformation not only translates this line segment to here, but it also translates all lines parameterized by rho theta with the same angle and same distance. Okay. So then, if I try to find, I have no more colors here. So okay. So if I want to find the number of intersections with some line segment L rho theta with this given line segment, that is actually equals to count the intersection with translated line segment with translated curve, translated straight line. Okay. So rho minus 1, theta minus pi over 4, right? Okay. So does the number of intersection change by rotation and change the distance? No, it stays the same. Okay. But the problem is, since we are integrating over theta and rho, maybe the Jacobian could change, but we computed that the Jacobian is always the same as 1. So if you take the number of intersections, ni rho theta, this is between Ci to Ci plus 1 and the L rho theta. You can take ni bar, let's introduce another notation. It's the number of intersection between this 0 Li cross 0 and L, let's say L rho theta again. Okay. So we have this relation between ni and ni bar. So if you count ni rho theta, this is equals to ni bar rho minus 1 rho minus pi over 4, right? Because we are translated everything back to here. But if you range your rho and theta to the entire range, like rho is always 0 to positive infinite, and theta is from 0 to 2 pi, it covers entire cases. So the function is different, but the value is equal as long as you substitute your rho, this is theta, and theta. So let's try to compute my ni bar of over d rho d theta. So that is equals to when I translate, substitute rho bar to rho plus 1, theta bar plus theta plus pi over 4, then it's equals to this, right? So if you interchange this, so let's say, yeah, right. So basically, I want to compute this, but then I have to substitute that here, right? So this this serves as rho bars, okay? And this is equals to rho. This is equal to theta, okay? So then I have equation of Ni instead of Ni bar, but then I have to introduce the Jacobian. Jacobian of rho theta divided by rho bar theta bar d rho bar d theta bar. Okay? So what was this? 1. Now you have to actually take back to rho equals to rho bar minus 1 and so on. So this is 1. So this is the number of, count all the number of intersections with this line segment with any configuration of rho bar and theta bar. And this is also counting multiplication, count the intersection with any configuration of rho theta. So the bounds are the same. So rho theta always runs for entire range, and rho bar theta bar also covers entire range. So you don't have to worry about changing this domain. It's always the same domain. But we see that this is equals each other. It doesn't matter whether you take Ni bar or Ni. Okay?
If the bar notation means the right side of the graph,
Right. So,
I think it should be -1.
no, I mean this Ni is for this left-hand side.
All right, but I mean you said the bar rho is equal to rho plus 1.
Yes. Because I want to express my Ni with some sorts of rho bar and theta bar. That's here. If I express Ni as a rho bar theta bar function, then Ni bar is given by rho bar minus 1 and theta bar minus pi over 4. I'm going to replace that into theta, rho and theta. So that's how I get the rho theta here. Right? So this Ni bar is already expressed in rho and theta. I'm going to I want to substitute so that it changes back to Ni, function of Ni. Then I have to do the opposite. Instead of taking 1, I have to add 1, and so on. But actually, what you do here is taking the partial derivative of rho by rho bar. So basically, you do the same thing we did in the previous calculation. You take the partial derivative of rho bar minus 1 by rho bar, and so on. Okay? But anyway, what's the conclusion here? So left-hand side was the integration of Ni bar, which deal with the special case when the line segment is on the x-axis. And we have seen that this equals to 2 times of the length of line segment, Li. Okay? So Li is the length of line segment here, because if you translate, it doesn't change that line. So basically, this is equals to this, which is equals to simple integration. So I can, this is 1, I can just replace my rho bar and theta bar by rho and theta, because the symbol doesn't mean anything. So basically, I get 2 times the length of line segment in any place is same as the integration. That's this. Okay. It's a simple, actually. If you think about more carefully, it's a very simple argument because it's a simple translation by constants. Any questions? Any more questions?
그러면 그 대의 1을 곱하는 거 해야지만 같은 값이 나온다고 하셨잖아요. 그러면 1을 곱하지 않고 그냥 적분의 구간을 변경하면
Okay, so even if you change the range of integration, you still need the Jacobian. That's the essence of integration by substitution. You always you definitely you should change the integration range, integration domain with the new variable, and you need a multiple of Jacobian always. Okay. All right, so let's talk about line integral. Well, that's the hard part. Now it's the easy part. So, so once we are talking about the line integral, it's going to be a fun argument. So, we're going to talk about line integral and surface integral of real valued function, and then we're talking about the line and surface integral of vector valued function. So let's define a case here. So let's say we have a two variable function whose value is real number. Here's the situation. We are not going to integrate over the domain in two-dimensional space. We are going to integrate over a curve. So that means we have x and y axis. Here we have a curve from one point to another, and here is one surface, graph of this function. What I mean by integrate over this curve is I try to find an area under the graph over this line, not the volume. If you take the volume under entire graph, then it's a volume. We are taking a line segment and then try to slice this curve with a curved knife, and then try to see the graph of this curved surface. Okay. How can we do that? How can you find the area of this kind of surface? Let me write down this situation. So let C C be a parametrized curve such that this image lies in the domain of F. Okay, so it's well defined. take the area under, take the section of the graph of f over the curve CAB. So what I mean by CAB is the image of the domain A to B interval. So it's a set on XY space. So this is CAB, and usually CAB is abbreviated by simply C. Okay, because when we mean by C, it could be mean a function, a parameterized function, but since the domain of interval is fixed, so C can mean the set of range in XY plane. All right, how can you find the area? So finding area by integration in a single variable function is done by Riemann sum. You chop your domain into smaller pieces and take the small area of a small rectangle and then sum those areas to approximate the entire area. We can do the similar here. So you can start with a small segment of this curve. So and then try to find the rectangular area here, and then sum over all segments. So we take I from 0 to n and let Ti to be A plus I times delta T, where delta T is B minus A over N. Now, the area, so I'm taking a line segment connecting Ci as, take the line segment Cti to Cti plus 1. Okay, so if you're looking at the xy plane, although this is a curve, I'm taking a straight line segment that approximates this curve. Okay. For simplicity, let's use the same notation we did in the previous example, previous proof. So I'm going to Ci and call it Ci and Ci plus 1. Okay. So the line segment connecting these two, and then this will going to be the width of this rectangle, approximating the area. Okay. The area of small rectangle over this line segment, Ci plus 1, is what? How do you take the area of a rectangle? You first take the length of width and then multiply the height. So what's the length of width? Right, you take the length between these 2 points, right? And what's the height? You take any point in between ci and ci plus 1 and then find out the value of function at that point, right? So let's say so cti star, okay? So where ti star is any point in between ti and ti plus 1. So how do you find the length? Say, let's say ct is given by xt comma yt. So each x and y coordinate has parameterized by t. So ci is cti, so therefore it's x ti, y ti, and same thing for cti plus 1, y ti plus 1. So this length is square root of what? xti minus xti plus 1 square plus yti minus yti plus 1 square, right? So let's compute the total area. The total area is approximately sum of all area. So f cti star times square root of xti. Let's put ti plus 1 first. Ti plus 1 minus xti. Okay, it doesn't matter because we square that. So yti plus 1 minus yti square. Yeah. And then, so this is not what we want because this is an approximation. We want actual area. So before we send n close to infinity, let's talk about reformulation of this part. So I'm going to take ti plus 1 minus ti over x ti plus 1 minus x ti square and y ti plus 1 minus y ti plus 1 minus ti square. And you see, this is the delta t, okay? We have delta t square, and the square root, so we have delta t. So let's do more. So we have I from 0 to n minus 1, and fcti star, and then we have so we have an average rate of change that can be approximated by, not approximate, that there is a point that is aimed to the average rate of change where you get the actual rate of change, right? So you can say that this is x prime of t, let's say I have star already, so bar, okay, square. And also same thing for y function of y. Assuming that this x and y functions are differentiable functions in one variable, I can find a point ti bar or ti double bar whose instant rate of change is equals to the average rate of change in this interval ti to ti plus 1 and delta t. Now, to find the actual area, you take the limit n goes to infinity. What do you get? The right-hand side becomes integration on t, right? What's the limit of t? T changes from a to b, okay? A to b, and we're taking integration of function f composite c, okay? So c is a two-variable function. We are taking a value of two-variable function, but that point x comma y is determined by the point on the curve, and that is parameterized by t. So therefore, we have a function of t. And then we multiply that with these. So when n goes to infinity, ti bar and ti double bar gets almost equal, and it becomes the parameter t, okay? So when you take x prime, so let's write it here. So x prime t squared plus y prime t squared. And what's this? This is speed of the curve, parameterization of curve. So c prime t speed dt. That's the equation. That's the actual area. So it's very easy concept. So first of all, let's take a definition. So whenever you have a two-variable function, we usually write that as the line integral is written as this integration of f over c, the curve c. So this curve c means that the range of the parameterization curve C, which is from AB to R2, okay? So this is a usual notation, but you have to understand to consider this C as a range. And how we define this is you have to find out the parameterization of the given curve, which is just a set. But once you fix your parameterization, you can compute your integration, this line integration, by this formula. Because what we are doing here is we're not care about the parameterization. We just care about the area under the graph of function which lies over this curve C, which is just the curve, which is just a set. One remark before we finish is that so we do not specify to define the line integral, which means that only the shape of the curve C matters. That's obvious because if you want to find the area, the shape is the thing that we need to consider, but not the parameterization. But that means, but the weird thing is, if you really want to compute something, you need the parameterization, right? But the definition doesn't care about the parameterization. It only cares about the shape. That means the right-hand side of this definition do not depend on the parameterization of C. So you could find a parameterization of a curve in one parameterization and you have another parameterization, but it says that it doesn't depend on actual parameterization. Why? So let's think about you have different parameterization. Suppose C1 is a parameterized C1, C2. So basically, let's say both from, or maybe I can make it also different here. So we have C1 is from AB to R2, and C2 is from CD to R2, be two parameterization of C. So meaning that these two have same range. C1 is same as C2. Okay? If you consider the range as a set, it's the same thing. Then we can find by the way, I have to mention that if you parameterize a curve which follows in one direction, and then when I say these two are the two parameterization of the same curve, I'm not saying one parameterization is going back and forth and go to another point. We are just taking a parameterization which goes in one direction only. So there is no turning back, okay? So which means that if I say parameterize the curve, this kind of curve, let's say this is one parameterization. So do you see what I'm saying? So we have somehow we could have this kind of parameterization, right? So it's the same movement on the same circle, but this one is moving forward, always moving forward, but this one moves backward at some point and then move forward again. I'm not taking this kind of parameterization. I'm moving always the forward direction of parameterization, okay? So not this kind, okay? So then there is a function. Actually, this is a one-to-one function, one-to-one correspondence function. Let's say f is already used. So let's say function L from AB to CD. That means A to B, C to D, C to D. And then it's a one-to-one function, so it always goes in this direction. Okay? So if I have like going backward, if I have a going backward direction, then I should have a hump here, but that's not a one-to-one correspondence. Always increasing or this kind of function. So such that my C1t is equals to C2 composite LT. Okay. I can always do that because it's just a matter of how changing the speed of parameterization, speed of movement. If you have a same curve to follow from one point to another, and you want to have a different parameterization, you're just changing the speed. The changing the speed is changing the movement of time. So this A to B is the time period of C1, and C to D is the time period of C2. You're changing how fast the time changes on one parameterization to another parameterization. So you always have this kind of L function. And then let's try to compute the right-hand side for C1 and C2. So then if I take the C1 parameterization to the right-hand side of, if we use C1 on right-hand side of star, we get C1 is from A to B, FC1 and C1 prime dt. Okay, that's it. And then let's replace this C1 with C2, this composite L. So then we have AB. So AB is from AB is for T. Okay. Sorry, is that right? Yeah, AB is for T. Yes, I don't have to change it. So there's F composite C2L. Okay. And then C2 composite L in prime absolute value dt. Okay. I just replace C1 by C2 composite L. That's all. And let's try to replace this L. Let's say I want to write LT equals to H, okay? With H, I want to express my value of L with H variable. So that means DH is equals to L prime T dt. And if I take C2 composite L prime, so this is not a composite of single variable function. This is multivariable function. Although L is single variable function, you have to use the chain rule on multivariable function. But the multivariable function, the chain rule of multivariable function is the same thing. You just multiply C2 prime with L prime. So we're taking absolute value of these. Now, this is just a number, just a real number. Then this is the vector. So multiply a scalar to the vector. So when you take the size of this vector, you're taking the size of vector multiplied with a constant. So the same thing as size of vector, original size of vector C2 prime times the size of the scalar number. Okay? So we have split this part. And then let's look at this again. So, so this becomes, now I want to replace, okay, let's say AB, F composite, C2L, or let's put the parentheses in this way for now. And then C2 composite L absolute value is equals to C2 prime L prime dt. Right? So we have always a positive increasing, increasing function for L. If it's decreasing, then it's not a one-to-one map. Okay? So we have L prime t is always equals to L prime t absolute value. So this part is equals to L prime dt. So I can replace that by dh. Okay. And L is considered to be h, and I can change my range of t to the range of h because I'm going to change it to dh. So when t is changing from a to b, h is changing from c to d. So this is equals to f composite c 2 with h. So I can eliminate this, but I just wrote it. This is also c to prime h and dh. Now, I can I can change my symbol h to t, right? fc to t and c to prime t and dt. And what's this? This is the definition of the line integral using T2 parameterization. Where we started from the definition of line integral with T1 parameterization. We have seen that these two are actually the same thing. Okay? So don't worry about parameterization. As long as you parameterize it correctly, then any parameterization gives the same answer. So what happens when you move backward and forward again?
You get
Huh.
much more or less.
Right. You could have less because if you have a negative value function. Assuming that you have a positive value function, if you move backward and forward again, you have twice more integration of these intervals, right? You have a different result, okay? So when you parameterize things, watch out for the integration, parameterization. Let me give a very quick example and then really finish this class. So let's see, C is a unit circle, and I want to, let's say, integrate my function 1. Okay, so when you do the line integral, define the line integral, ds is the common term to express that it's a line integral. So first you have to parameterize your unit circle. So ct equals to what? How do you want to parameterize? Cosine sine, right? So 1 is always 1, so you don't have to worry about. So t changes from 0 to 2 pi to cover the entire unit circle. And then what you put here, absolute value of c prime t dt. So basically, if you take the square at prime, it's minus sine, but if you take the absolute value, 1, so you get 2 pi dt, which is 2 pi, which is the area, in the length of the unit circle. But basically what we have doing is that we are taking an area under the constant function graph, which is 1, under this unit circle. So basically we are taking area of a cylinder, okay, which is 2 pi. Just want to finish, but this is just a remark that I'm going to write here. We said that the parameterization doesn't change the line integral, but what if we integrate in reverse order? Instead of integrate over a to b, what if we integrate over b to a? Meaning that if I integrate in this direction and we have the same curve, but if I integrate in the reverse direction, what will be the result? Equal. Yeah, it's equal because we're just taking the area. But if you're talking about the line integral of a vector field, then the direction matters. If you integrate over this direction of the vector field, then it's a negative of integrate the vector field over the reversed direction. But we are talking about the integration of a real valued function, so it's always the same. Okay. All right, so let's finish here, and we'll see on Friday.